Hello everyone. I see that 6:20, so 4:20 on my clock, so I guess I have to start. I don't see any crew members, but yeah. Hello everyone. Thank you for joining to my talk about C++ 20 modules 5 years later. Quickly about me, my name is Mikhail Svetkin. I'm working at Remarkable. We're doing paper tablets. We claim that they're better than paper. You should absolutely believe us. And the areas of my interest and things I mostly work on is about architectural applications, internal frameworks, and some libraries, and build systems. That's partially explain why I'm into the modules, kind of. So we are going to talk today about what is the C++ modules, why C++ modules, what's the current status of them. We'll kind of summarize that. And then we'll talk about the build system experience and come up with some conclusions, I would say. So let's start with the simple. What is C++ modules from standard point of view? So I divided in two categories. First is language features, and C++ 20 when the modules has been introduced. And as far as understood is a couple of new keywords, module, export, import, even though export been already in the standard, but then it was removed if I remember it correctly. But yeah, there was a module linkage, which we will talk a little bit about today. And that's it, as far as I know. Correct me if someone knows better. From C++ 23, there is nothing. C++ 26, there is nothing. So the modules are done from the language perspective, which were cool. The second group is library features. And on C++ 20 level, there is nothing. C++ 23 introduced import std and import std.compact. So technically, this is the first module you're supposed to be able to use from C++ 23. And C++ 26 doesn't provide anything as well. So some of you might ask, and that's it? That's the whole thing? What's this about? And just to clarify, like in essentials, what are the modules and all these new words? Is it about replacing the includes with import? And replacing DLL export, DLL import attributes, like export macros with export keyword. That's in essentials what a module is about, I think. And that's the whole my research was about that. And mostly people will face these two words, import and export. Let's go a little bit forward and ask why C++ modules? What are the issues with headers? Because we saw that import and export replacing basically headers in a way. So if you Google it, you will get, or ask ChatGPT, you will get something, headers leads to slow compilation. And the reason would be that every source files have to be, like on every translation unit, you need to include all the headers, reparse them, blah, 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 blah. It will tell you fragile dependencies, and we know probably everyone faces it. Sometimes you forgot to include something, or you include too much, maybe some macros collisions, and so on. So, and there is a leak in internals, is basically the headers expose all the details about what's in the header, something that behind the namespace details or some implementation details, which technically you should never ever see and should never ever try to touch it. So I'm going to show some examples of all of these issues. And for that, we need to take some C++ project to play with. And I will take modern C++, even though the word is abused as I learned yesterday. So maybe I need to redo it. But the reason I said modern because I gave a talk 2 years ago about how to start modern C++ project. So maybe I need to do a new one, how to start a progressive C++ project or something like that. But anyway, I took this example as a modern one. So we have a cool print, we have a std.println and new hello world. And then I tried to compile it with GCC, it worked. With Clang, it worked. With MSVC, it didn't work, because for those who didn't know, you need to source the environment variables, and then it works. And then I even tried this Clang wrapper of Microsoft MSVC compiler that worked as well. So when we talk about the first point was about slow compilation, it's kind of build performance, right? So let's actually see what do we actually include when we just say print. So you can ask the compiler to tell you actually what does it include. Every compiler has its own flag in gcc-m, and you can generate the include txt. Anyone guess how many includes we will have? 1, 2, 5,000, 1,000? Depends. That's a very good answer. So on my PC, when I tested, it was 168 with GCC. I didn't look what kind of them, but that's some kind of system ones, I guess. Maybe some other internal details. And what do we actually compile? Because if we include all of these includes in one file, what is actually the size of the binary? Or the source file will be. So again, you can ask the compiler, give me a preprocessed file, and I wouldn't ask you guess the size, but the size will be 1.7 megabyte. Just for simple print and hello world. We didn't even compile anything here. We just say, give us actually what do you want to compile. And so for the GCC, it was 168 includes. 1.7 megabytes is the total size of the file. For Clang, it was 202 for some reason. And it was 1.8 megabyte. When I tested on MSVC, it was 124 less, but apparently size was much bigger. So 2.6, almost 2.7. So if we compare, did I skip the modules? Sorry? Oh, sure.
Yeah, for Clang, you used lib C++?
No, it was a steady lib C++. So it was GCC1. I don't know why. That's why I asked. I said I don't know why it's two more. But yeah, so when I use the Clang, I actually build with a GCC standard library. So I don't know. Yes, I agree. Fully agree. But maybe it has some if-defs or something which caused it. I don't know. And unfortunately, it seems like I've deleted the one slide where I replaced that with import std. But I can have a second slide which actually says the difference. So just trust me that it is. So if you compare with modules, you will get as an include file only one file, which is your module. And the size of preprocessed file will be just the code in your actual file. I don't know why I deleted the slide, but that somehow happens. Just to visualize the problem, I will try to do a smart animation. So let's imagine that we have a CPP file, which does one include, which is print, and then we have our some kind of code. So first, when we try to, the pipeline of compiling the file, first we invoke the preprocessor, which tries to locate all the includes, find them, read all of them. Then it's try to compose them in one file or in memory, or doesn't really matter. And only then we actually can start to compile. And when we do compilation, we actually need to parse everything what we combine, right? Then we're building the AST, abstract syntax tree. And then we actually do code generation. So, and that's what we do for one file. If we add more files, then technically we do all the same steps. And let's just, in this case, we just do added two more files, B and C, which is also include just print. And you've noticed that these pre-processing steps, they are the same. And we do exactly the same stuff. And we cannot share that state between these translation units or when we basically compile them. And we also need to the same parse that long, big file. And then we can build AST and do code generation. So if we add plus 100 CPP files, we know that our projects are not small, right? Everyone has millions of CPP files there. So there come up, then we can think about interesting questions to ask. Kind of. How often print is changed, the header itself. How often do you change your compiler, right? Not that often, I guess. Most of companies stay on some version of compiler for ages. And the same question, what about the rest of this from 168 to 120 files? They're not changed, but we build all the time, right? Remove our build folder, we build it again several times per day. But we do all this unnecessary work all the time. So yeah, question, why do I need all these steps? And another one, how modules solve it, basically. So try to do, again, smart animation or diagram. So let's imagine that we have a CPP file, which instead of doing include print, does an import of std. So technically, we should have a preprocessor invoked, but there is nothing to do. So we can jump directly to compiling. We have a new step which we need to do. We first need to, compiler need to find that module and load it. But that's not a big problem. And then we need to only parse the user code. I highlighted the user code because the module itself already pre-built. Every compiler implements it differently, but we could assume that the module itself is already has the AST there. So you know everything. You don't need to parse it. So we only do parsing of user code. And then we do building of AST of that, and then we do code gen. So we can remove this preprocessor step at all. In practice, it still is there, but it just does very little. So then if we add more files, we again see they only need to load the module. We don't do all these steps. We're parsing much less. So that's basically theoretically where the speed comes from. The only one thing is the difference to the headers. Before, here, 1 second, here, we only, when we do include print, we take the file and we don't actually know was the library compiled or not, so we can do it in parallel. In a way, that's how we speed up our build currently, right? With modules, there is a small bottleneck, which is people claim not that important. But basically, you need to first build a module. So someone at the beginning has to build your std module, and then you can consume it, and then basically, So first you build a module, then you can build the rest. But again, once you build std, how many times you're going to update it? Not really. So you build it once, you save it there, stay forever, so that's kind of once, in a way. Of course, you need to put it somewhere in a good place, but yeah. Implementation details, I would say. So my synthetic tests and benchmarks, kind of. And remember, Klaus says that never ever try to use it against me. It's just my benchmarks. So if I take 50 CPP files, we just do one include and try to compile them, it takes on my machine almost 2.6 seconds. If I do import std, it's a little bit faster, 2.1. We can say 20% faster, right? Then I take 100 CPP files with include. It takes almost 10 seconds. With import std, it takes 3 seconds. So you can clearly see the more files we compile, the faster it gets. Also, I have to notice when we do import std, we're actually importing the whole standard library. Here we just included one print. So for example, if you include vector, the speed will, you will see the difference more. And I think, 38% faster approximately. But this is a synthetic, not that more interesting, not very interesting to see. And I want to hop over to the Boost module support research. How many people know that Boost is actually working on it to support modules? 2, 3, cool. Yes, but yeah, they have this blog post where I can read. It's pretty nice, explaining what's the challenges, what's the issues, what's the bugs. I will just highlight few of things here. So in the second blog post, they've noticed it, or they did a benchmark. So they took the import std, they built it. They took the Boost SEO, they built it. And then they was trying to build some project with it. And you can see the more translation units there are, the faster it is. When you have seven files, you get with modules, it's 10 seconds. With headers, it's 17. So almost, we can say twice, approximately. So it's getting faster, right? The more interesting was to read the third blog post, is that did the benchmarking on the Boost MPP11 library, which have a test suite consistent of 200 translation units. And there is the speed up is quite significant. With the headers to rebuild it, it took 2 minutes 10 seconds. With modules, including building actually modules, it's taking 39 seconds, which means rebuild for the modules will be even faster. That is a significant improvement, and I'm quite sure everyone writing tests, right? Everyone has millions of tests, so building them is getting much faster, which is good. So on that note, I would say modules are faster, and so they reduce the build time. It is a fact, and you can see as people report it. However, it depends on the project, how your code organized, and so on. So let's go to the next point, fragile dependencies. If I show you this code, is there anything wrong with it? Is it well C++ written code? For the recording, audience is silent. That means everyone thinks this is a good code. So if I can try to use that code in my main, and I compile, it actually works. So again, still no one see the issue. Good. If I highlight like this. So our foo header using std string view, but it never included string view. We got it transitively from including print, right? So if I swap around them accidentally, maybe Clang format will do that for me, suddenly I cannot compile anymore. Even though that particular file looks like okay, just changing the order, make it. And also like print includes somehow string view internally. And I'm not sure if it includes on every platform actually. I actually tested it only with GCC. Hmm? It has to, okay, so good. But maybe it does forward declaration or something like that. Get it?
Implementation are allowed to do that, but
yeah. Okay. Good that all the standard libraries agree with it here. That's good. But if it takes something else, another include, then it may be different. So some of you might ask how the modules kind of solve it. And the answer is that if we just replace our foo with import foo, and it doesn't really matter where you put it. Remember I said the first we need to build the module. So first we build it. So it's already done. So it should know about everything before. So then it doesn't matter where you put it. It already contains everything. It knows all the types kind of. Yeah. So in that regard, no matter what, doesn't matter what's the order, you can check is that if your module is correct inside the module kind of when you build it. Leaking internals. I was trying to come up with a good example, but had a bad time. And then I thought about this one. I'm not sure if it's a good one, but is that code correct? Correct. It's just a static assert. I'm checking if it is integral. It is correct. It compiles. If I do like this, if I ask if integer pointer is integral, is that correct? Yeah. Yes, it's correct. What if I do like this? What if I inject my code? Even though everyone knows that you should never ever inject anything in std. But maybe, but I compile and it works, you know? On my machine I got an error. Suddenly, integer pointer becomes an integral, right? So if I'm working on one compiler with one version for the one time, for the whole time, maybe it will work all the time unless I update it, right? So technically speaking, you should not ever do this, but you can, because by including the headers, you get access to all the nitty-gritty details. You can do wherever you want. Sometimes you do it by mistake, sometimes you do it because you have to, like probably some of you already in your projects sometimes access to details namespace, right? Because that's not a public API, but you have to use it, right? You shouldn't, but you do. So that's the situation here. With the modules, if we just again replace it to import std, this line becomes illegal because you cannot anymore, in module worlds, you can actually say, I don't want that part to be visible. So then you cannot actually compile, you cannot access that, which is quite good. Now all your details is hidden, no one can access them. So yeah, so let's just quickly summarize. Modules are faster, they give you speed up of your compilation. Depends on your project, but from 20 to 70%, which is good. No fragile dependencies now, include order doesn't matter. Wherever you import one module, another one, it doesn't matter, which is quite good. So no missing includes, no order of inclusion. Yeah. No leak internals, only public API is visible, and implementation details stay hidden, which is quite good. I think by that moment, you should everyone say, yes, I want a module, right? No? Okay. Tough crowd. But anyway, we will write a module, the simple one. And we will go further and further. And we will learn through mistakes. We will do a lot of mistakes to write the module. And let's start with a very, very simple one. We have a module declaration. This is how you declare a module. In the beginning of your file, you write export module and the name. And the rest is like a module implementation. I'm not sure what's the right name of it. Probably Daniela could correct me, but I'm not sure what's the right one. I just call it implementation. But that altogether is purview as far as I understood. But these terms is a little bit hard for me. I tried to read the standard and sorry, it's hard. So, but as far as I know, this is what they call purview, I hope. And Daniela, you can tell me later that I was wrong. Yeah. So then in your main file, you can say import foo, and you say include print, for example. And you see I'm actually able to mix them, which is quite good, maybe. But for our talk, we will mostly focus on just say import std. We don't really care about mixing includes. So then, oops, did I highlight it already? Sorry. Doesn't matter. Yeah, I want to highlight is that two things. I don't use any more compiler directly because it's almost impossible to remember all the flags you need to pass to the compiler. So we just assume we have a build system to solve it for us. And the first mistake, I already accidentally highlighted that foo is actually has not been declared. So this is our first mistake. Is even though we have module called foo, we imported the foo, there is no namespace. Modules by default doesn't give you a namespace. They're not kind of scoped in that namespace. So you have to manually say namespace foo. Now, do you think that's enough? Yeah, see, someone says no. That's right. So if we try to compile again, we'll say version has not been exported. And this is the example where we basically doesn't allow to access anyone to some hidden out details. You need to manually say what you want to export. And then you just say export, and you can export whole namespace. You can apply it for function, for template, outside of namespace as well. So if you don't have a namespace and you say export version just as a function, then it will be in global kind of namespace. So it's pretty good. So we need to explicitly, now we're able to explicitly manage what we want to export, what we don't want to export, which is good. So now if we compile, finally our application works. We get our version, which is good. Now let's look at the integer we have. Version is not just one number, right? We need something better, like a string view, return the proper string. So, and now, since I remember I said that modules should know about all of these symbols and what the string view means. So you might ask how module knows what is the std string view. And the answer it doesn't know, you have to tell it. So you need to import std. This is the place where you do imports. And now if you try to compile your code, it will work perfectly fine. Cool. So question, what do you do if the compiler does not support import std? Because it was C++23. It's, so if you're just using pure C++20, you are not able to do that. Your compiler is
It is allowed.
allowed.
All implementations do it in C++.
Okay, I didn't know that. But let's assume your compiler did not provide it, right? It could, right?
It's an extension.
Yes, yes. But I just say my version of the compiler is too old. It doesn't have that cool feature. So can we just use include string view? And if you try to do that, depends on the compiler, you'll get some wall of text, something bigger, something smaller. But basically, remember I said module linkage, and this is what it means. Everything what's after export module foo is part of the module. So in that case, the string view which would be included, it would be like defined twice, one in the standard library and one in your module. And then you get ODR violation that it's not allowed to do that. Yes, so don't do this. But so what to do, the workaround is to put it in a global fragment. There's special place, again, in the beginning of file, you can say module column, a semicolon, and then you can do your includes. That's the place where to include stuff. And again, that's called purview, and that's a global fragment, and altogether called primary module interface. There's so many terms of this. Yeah, I don't think you need to remember that. I just try to highlight. Anyway. Okay, let's go forward. What if our module getting is too big? What if we have 10K lines of code, right? Can we split it as we did with headers and CPP files before? Or everyone keep having these big files, right? So the answer is yes, you need to do a partition, it's called. So you need to say magic spell export import column version. And then you're saying that your module has a partition, like a part version. And then you need to create a file, say that I am a partition of module foo in the beginning, and then you can do everything. And you can notice I did not put the includes, because this global fragment is only allowed in primary module interface, and you cannot do in the partition module interface. So that global fragment is shared across everything what's module belong to, as far as I know. I see that Daniel, no, it's not. I compiled it. Okay, we can talk later about that. But that's how I understood it, and it worked on my machine. Okay, awesome. I want it.
Partitions don't take dependency on each other.
What?
Partitions don't take dependency.
Okay, I believe you, but I can show that it works on my machine.
Yeah, maybe it's an implementation.
Maybe. That's the problem with C++, right? So what's the current status of that feature? And this is where we're actually coming to that, what you said right now. It's implementation deal. So we have a compiler support, and we have 3 of them, right? We have a build system support, and many of us using different build systems, right? There is package manager support. There's ecosystem, and by ecosystem I mean library adaptation, tooling adaptation, and there is also a little bit of user experience, right? Not everyone knows how to do that thing yet. So let's look at the compiler support. And I tried to search in public sources. So C++20 modules, as far as I understood, supported by GCC 14, Kelang 16, and MSVC, wherever numbers there. I don't know how to understand MSVC numbers, by all means. But yeah, I haven't verified all of these compilers, but if you go to the compiler support, it claims that basic C++20 modules should be supported by that versions. I don't know. C++23 import std was officially by that page, says from GCC 15, and that one I verified on my own. Clang 17, I tried only with 20. And the number from MSVC again. If someone knows how to understand MSVC numbers, please tell me later. Okay, good. And there is one big problem for us and Remarkable. We're building software on all platforms, including the Mac and this thing, iPhone. So Apple Clang is very sadness. Even though it says Clang, which is supported from 17, but the Apple Clang doesn't have anything. It's just like, I don't know, they specifically disable it for some reason. If someone knows, please tell me later or speak now. But yeah, so if you have Apple Clang in your build environment, just forget about modules for whatever reason, I don't know. Yeah. Okay, let's look at the build system. And of course, there is the best build system, right? CMake. Yeah, I see people nodding yes, but no. But apparently, CMake supports basic modules without import STD from 3.28, and 3.30 has experimental support of import STD. MS build, I couldn't find which version supported, but it claims that it's supported. I didn't try. The Mason has some experimental support. Basil claims has experimental support. There is build 2. I'm not sure how many people use build 2. No one in the room? Good. But it claims that it's done it 4 years ago. Maybe. But at least the article which claims it from that date. Okay, let's go to the best build system ever, CMake, right? So let's look at what we actually need to do in CMake. So now we have a new magic spell. We call file set xx modules files foo cpp m. I'm just highlighting that it's module. You don't have to say it's m, but it's just easier for, it's like it's not just a cpp file, not a regular one. And then with giving foo cpp m, we have the global fragment, we're exporting module foo, we're exporting num space. It should work. And then you just say add executable. In CMake, you just treat module kind of as a library, no differences here. So just say targeting libraries private foo. And then in your main CPP, you can say import foo, include print, and sure, compile. It works. Great, right? So technically, it's usable, but with caveats. I think you need to have the latest, greatest compilers and latest, greatest CMake. That experience would be really good, in my opinion. Because I tried different versions, it was a little bit not working out of the box. Even though they claim that experiment of just modules is ended, but I think there are still bugs to follow up. Adaptation. How many libraries support modules? It's a great question, and it was partially answered already by Mikhail here sitting. There's an amazing website, Our Modules Yet. If you haven't been there, it's a nice, well-designed website. I like it. And it basically says, it's probably very small and hard to see, but it basically says that out of 2,441 projects, only 46 is supported. So almost getting to the 2%. It says 8.7 projects per year, and estimate that we will done by, yeah. Sadly, but it's true. However, which libraries support modules? You can go and again scroll a little bit down on that website. You will see a list of libraries, and you will notice that most of the common, cool, modern libraries is there. So it's getting, adaptation is getting. That's what I was trying to say. Again, there is this Boost research, as I mentioned, and if you don't want to read the blog posts, which I would recommend you, I'll just tell there are. Modules are usable, that's the conclusion. They speed up builds. There's few issues with MSVC and CMake, and apparently Boost is going to support modules. There is only one strict requirement, as far understood, is that it requires C++23 and import STD. Because the managing is that you need to include or imports, it's complicated. And as far as I understood, they said no. So if you have import std, then you will be able to use Boost as a modules, which is quite cool. Boost, one of the biggest projects, right? And there are on that website, if you see, there are already a couple of the Boost libraries. There's Boost PFR, Boost type index, Boost any, Boost regex. So they're work in progress. Yeah, I think they're waiting for a couple of issues in MSVC and CMake, and then they can continue. Package managers. They should work, right? And I have to say, I Googled it, I tried Ask ChatGPT, I did myself, and it doesn't really work that much. In VC Package is a little bit twisted story, because VC Package doesn't actually build stuff that much. It's called CMake to build stuff. So apparently when CMake is ready, library is ready, it might work. But there is no good article which is like, this is how to get, for example, FMT to work. With Conan, I couldn't find any particular information of how to do it, so I assume it doesn't work. And then I found this talk from Luis. He works at JFrog, which is, as far as I understand, develop Conan. So he has like an amazing talk where he explains why is it hard to support modules in package managers, what's the challenges. And yeah, in this particular slide, he explains like wherever you produce your module, then it's like you cannot actually share because it's so affected by what version of the compiler, what is the environment variables and so on. And then if you try to like build it in one machine, put it in a cache, restore it, then it just crashes. And he has a couple of slides where like, what are the errors? So go and take a look. Oops, sorry. So yes, package manager doesn't work. And if someone is really want to try it out, is there any workaround? There is, again, CMake, there is a fetch content, which apparently works because you do fetch content, and fetch content is getting your part of your regular build, and CMake knows how to build it, everything inside. So just a small example how to do it. You need to set the minimum version, and by setting the minimum version, you will tweak the policies inside the CMake. You also need to set the experimental CXX import std, and that value which you see there is changing depends on the version. Then you can say CMake CXX module std1. Then now it knows that I can work with modules. This is experimental, right? Then you can fetch content FMT, find package, and build. And that's pretty it. But again, don't recommend, but if you want to play it out, try. On my Mac, I spent like 3 hours to make it work because apparently my Clang was not okay. I used the homebrew, it didn't work as well, so I have to build from scratch the Clang, not the right version. I forgot to build libc C++. Yeah, on Linux and GCC, it's much more pleasant experience. Yeah. Tooling. So I'm not sure how many of you had an expectations, but modules aren't compatible between the compilers. Everyone went for different flags, the simple one, different binary representation. So wherever you build your module, you cannot reuse it. And apparently by watching the talk from Luis, I actually even learned that even if you build, like if you take the GCC 15.1, and then you get 15.2, then it's incompatible as well. So even inside the compiler with a different version, you cannot use them. Which leads to a couple of issues. Clang D module support. Most of the IDEs right now using Clang-based tools to do after completion and so on, right? So Clang usually compile commands file, right? And it needs to understand these flags, right? But now they're different. So for example, if you build your project with GCC, your after completion is not going to work because now the compile commands has flags which Clang cannot understand. And even if you're smart, you can update your compile commands file, replace the flags. Now the binary representation is different, so Clang cannot use them. So Clang have to build it by himself. So which is not yet done, and that link, I share my slides, so if you press it will lead you to the issue in ClangD, which explains probably either they will try to understand the GCC flags and they will try to build in the background, but they have not decided. And that happens because C++ doesn't have this standard about ecosystems, how it should talk together, kind of. And apparently there was a proposal to create C++ ecosystem international standard. And if you go there, I think the latest update was 2024, and I'm not sure what happened there. Seems like it didn't go. Okay, that's sad. It was said that it was abandoned, yeah. But that was, as far as I understood, the idea is to actually, let's have a standard way to tools talk to each other. But sadly didn't happen. Okay, user experience. There is a lot of new errors to learn. Some of them is more readable, some of them no. There are bugs in compilers. They are fixed quite fast, but still you have to learn. And that we all need to learn. So no more something like that where you can just simply invoke your compiler, pass the std flag, say this is my version. Because for example, if you do import std, it doesn't know where it is, so it's need to build it and so on. So maybe later it could be improved, but that doesn't work right now. That will not. On my GCC. Yeah, maybe. Again, different compilers, different user experience. Which leads a little bit, if you use the Godbolt and you want to do import std, you need a template with like CMake, for example, to help you to use import std. You can Google it and you'll find there is a lot of links on internet how to do that. Okay, let's just summarize. What is the current status? Compiler support is almost done. There are things which missed, but I think general purpose use, it's almost done. And as I said, Boost is going to support, which is good. And this is their conclusion as far as I understood. So build systems are ready-ish. CMake works. This is the best build system in the world, so we don't care about rest, especially if you have your own build system, right? So ready-ish. Package managers are not ready, but see the work in progress, so probably it will be there at some point. Libraries are getting ported, even though estimation is quite bad, but you will see that more and more libraries actually get ported recently. So, and I think right now is a lot of research how to do it, how to keep being a library with the headers, and how to be with the modules. So as far as this path is well understandable, and I think the three biggest library like pushers, FMT, MP Units library, and Boost, it seems like they found a way to do it. So yeah. Tooling support is work in progress. As I said, probably it will be there at some point, but yeah. User experience is different. It depends on the compiler, depends your setup, yeah. So should you start to experiment with models? I would say yes, you should. And if you don't want to do it in production, I can understand. Just go to that website, pick up wherever the library is there and try. First you do to the community. You can do a PR, right? You learn, you do a PR, maybe yet one more project. If everyone in this room does a project, we will be there, right? Quite much faster. And then maybe you can use it in production. You will actually learn that you can use it in production with your setup. So really recommend. Should you start to switch over modules? I would say yes, but with a lot of conditions, and I will just list few of them. So you don't need Apple Clang. That's the sadness. Easier if using single compiler. Like if you have one GCC version which you know you stick and you can build yourself, perfect. Or Clang, doesn't matter. And again, only if you have a full control of the build system, of your build system. So if you know that you can fix the stuff and yeah, you can update the build system, maybe rebuild it, patch it, and there's some you're ready to accept tooling limitation. That is, like as I said, if the code completion for you is not that need, and you have a ChatGPT or wherever this nowadays AI can do after completion, maybe you don't really care about that. Yeah. So that is summary about the modules in general. Now I want to go to the second part of my talk, where I want to talk a little bit about build system experience. It's completely disconnected from that part. It's mostly we now want to learn what the modules are, but I want to focus on the build system experience with modules. So let's take a look at CMake and C++. First of all, we need to define module name in so many different places. We need to say add library foo, file foo, export module foo. I mean, you could call your file wherever you want, but I guess it would be kind of weird if the file is called boo and it's export module foo, right? So many repetitions here. We need to do a manual namespacing. It's kind of, what if I forgot to do that? What if I do a typo? And the compiler gives me an amazing compiler error, which I cannot read. So, nah. And for example, when we do split our module, we need to so many manual work. We need to add the file to the CMake. We need to tell in our foo CVP that, yeah, we have a partition version. Then we go to that file and say, yeah, I'm part of that. Like so many, again, repetition here. So too much boilerplate on both build system and source code. And that's the way we kind of repeat it, two things. So maybe there is a better way. What? But yeah, it's Cargo and Rust, right? So let's just compare side by side. So on the right side, we have a Cargo. That's what you need to do to define a simple project, simple library. On CMake, that is not minimum. This is like, it's not even valid if you just do that. You need much, much more. But I just simplified it. Just assume this is the minimum. Because you didn't say CMake minimum version, you didn't define the project, you don't handle the installation parts, nothing. So, yeah, but let's just assume that it's minimum. And then we have some magic spells here, right? We need to have a file, we need to tell exactly which file. On Cargo side, we don't even say that. And we need to say public SXSTDs 20. This is for some reason for CMake, doesn't matter. On Cargo again, we don't do anything. Now let's look at the code. On the right side, we have Rust, which just defines a function and says it's public. On a C++ side, we need to say, I am a module. I am importing std. On Rust, you don't do it because the standard library is pre-imported. And again, you don't need to define that you're a module because it does then cargo.toml. You kind of module. And then you don't need a namespace. On C++, you need a namespace. In Rust, it's automatically again, so you don't need to do. And then I just compare if I just decided again split our module in a couple of files. That's the amount of stuff we need to do for CMake, new file, tell the CMake about that, and repeats that. Right on Rust, we just said, I have another file, and just move it there. I think it's quite visually visible how many changes you do in Rust. And again, we didn't touch cargo.toml. We didn't tell our build system anything. So let's just summarize the Cargo experience. Module declared once, just in cargo.toml. We get automatic namespace. Adding new files, we are doing via source code, not for the build system. And it's significantly less boilerplate, right? So if you wonder how it works, I will do again trying to do a diagram here, how it works. So when I say cargo build, it reads the cargo.toml. It's resolve your dependencies, so basically it's go and fetch all your third-party dependencies. It run build rs, it's kind of a way to customize the build points. I'm not sure what's the order here, resolve dependency or run build rs. That's I'm not sure, but I don't think it's very important. And then it compiles the dependencies. And then it says, okay, now I'm prepared the setup, I'm ready to build. But I don't know what to build. So we need to figure it out what to build. So in Rust, if you make a library, It's an entry point for the build system to scan source lib.rs. And then it learns that it depends on version.rs. Then it scans version.rs and learns that it depends on nothing. Now I know the build graph. I know what to build. Now I can build. So, and now an interesting question, maybe C++ modules can help us here somehow, right? That's the whole point. I was leading to that. So basically the thing we're missing, we need a way to scan source files to understand what it depends on, what it requires and provides. So the compiler flags for includes doesn't provide necessary information as we did before. And officially C++ 20 modules doesn't provide any mechanism. So, but there is this proposal which is part of ecosystem, but it's not, so it's just there in papers. And I think, but the cool thing is that it's been implemented by all the compilers. All compilers agree that we will do this. So what you're getting is that if we're having this full CPP, and you can ask Lang to scan, and you say format, and then you pass the all flags how to compile your file, you're getting such a JSON output, where basically if you see, it tells you, oh, this file provides interface, like primary module interface, and its logical name foo, and giving you the source path. And it tells that it requires std, which is cool. So, and all the compilers has different ways to invoke it, but basically you can ask the compiler what my file provides and what it depends on or requires. And then if you, for example, we split our file in two and we have one partition, then it will tell you that I require a partition of that module from that module. And then that the partition, you can ask again, and you will tell, no, I'm not in interface, I'm a partition. So this is my logical name, and I require std. So now we have a way to do the scanning, right? So potentially, maybe at some future C++, we can say CMake build, maybe it reads CMake toml, maybe it's resolve the dependencies through the package managers. Maybe it's even called build CPP. I'm not sure if it's a good idea, but let's just assume. We compile dependencies. We already build our library now. We can build the module tree, right? We can scan libcpp. It depends on version CPP. Let's scan version CPP. It depends on nothing. Now we can build. So I saw some people like, is it possible? Does it work in practice? And there I need to show a quick demo. I'm not sure if I have 7 minutes. Let's see. And I will try to do my best. Should I zoom it? Or is it okay visible? Yeah, just in case. So let's imagine we have import std main as a simple one. And then I call CMake build. It building, running, and running our hello world, right? And this is the whole, you can see the whole source. There is no CMake list, nothing. I didn't implement CMake toml. I didn't spend time on that. But I prepared this full library. And I can prove it that it's not building by writing some. Right, it's not built. So now the libcpp contains one function, hello, we're exporting it. Notice there is no any namespace, no declarations, and so on. So now if I go to my application and say import foo, and say foo hello, you'll get hello world from module foo. So that mechanism is actually working. That's my demo I want to show you. So you can say foo. The build system can actually scan it, cannot get it, and you can build. And we don't need all this boilerplate stuff because you actually can generate them through your build system. So just an example, I prepared the file called version CPP. So let's just say that, we need this export import column version. And don't forget it's a live demo. If something doesn't work, it's just a demo, right? And I just added in the version CPP that's some wrong code, right? So try to build, we get an error. Now we're actually building that file, before we didn't. So now let's just write a function, I don't know. It's a version, right? version, return, return 001. Okay. And then go to our application and say full version. So if I type everything correctly, it should work right now. Yes, we get it. So I was thinking if I had more time, we could have a name of the module, and we will show you this is not a pre-built stuff, you know, it's not fake, but we can do it later if someone wants. Now quickly back to the presentation. Yeah. Just want to highlight that's what you saw. Technically, I didn't implement CMake Tomo, but doesn't matter. Technically, that's what we got. And if you see, it's pretty identical to the Rust. So C++ can be cooler from the build point of view. Nothing stops us. That feature is there for 5 years. It's just lacking of particular implementation, porting, good support, and so on. But it's possible. And again, if we split it into several files, it's pretty the same. The syntax is different, but it's there, which is quite cool, right? And if you think this is just me, actually, there's been a talk at CPP now from Vito. He was talking about module CMake 3 version and 4. What's the changes? For those who doesn't know, he's a developer, one of the developers of CMake. And I've had a chance to talk to him there. And he actually said it himself that they're looking forward to somehow go to the cargo experience. So this idea is actually brewing. I'm not sure if they're doing it or not doing it. I've just decided to try. Is it possible? And it is. So let's come up with the conclusion of that part and combine it to whatever I presented before. So modules are getting ready to use, which is good. Modules drive ecosystem and the language further. Now we don't need this macros, we don't need this includes. Now we actually can tell. And there is a lot of cool talks I've seen about like what you can actually do with that binary information once you have a module, which is someone even proposing that you can do a kind of reflection by analyzing that binary format, which is quite interesting. Yeah, so it's time to experiment with them and use if it's possible. And then, you know, when you use them, you report the bugs, the chance that it's fixed is quite bigger. So there is a lot of movement right now, in my opinion. And the last couple of slides. Tomorrow there will be one talk by Alexander, which is sitting there. He will actually talk about similar topic. And I think I will go there. I haven't seen his talk, but I'm quite curious what did I miss. So if you didn't understand everything what I said and want to repeat, please go there. And maybe he will highlight even more than me and fix my mistakes. There is another talk at 3 tomorrow by my colleague Nicole. It's mostly for those who, okay, we don't have modules yet, but what to do? And I still have CMake, and it's terrible, right? But she will tell about what we do and remarkable to make it basically usable, user-friendly. So yeah, please attend both of these talks, and thank you and questions. Yeah. Yes, Danielle.
Is there a reason why you left out the other half of modules?
The question was why I left the other part of the modules, because you mean header units, right? And there is a private fragment. It's not really supported, and my whole purpose of the talk was to show what you can actually do with the build system. So I was explaining what is the modules, and yes, but there are missing parts, but I don't think that they're so important.
They are.
Okay, that's good.
The reason is probably because CMake doesn't support it.
Yes. Well, it compilers as well, right? The header units is not supported by anyone, or they do. Okay. Right. Okay, I didn't know that. Okay, good.
Actually, you can do more with header units.
Cool. Thank you. Oh, you will give a direction. One more reason to go to Alexander talk, to learn actually the rest of the modules which I left over and didn't talk about. What? CMake is de facto build system, but I agree with you. Yes. By the way, which one was the decent one?
Yeah, for example, XMake or MS Build.
XMake is a good one. Yes, that's true. Yeah. MS Build
Yeah.
on my Linux,
For a couple of years.
on my macOS or my Linux. Yes. Okay. Yes. Decent operating system. Right. That's true. Okay. More questions? Yes.
Do you think modules would have been useful earlier if we had a proper ecosystem specification in the standard?
So the question would have been use modules better if there is a system ready, but I think yes, but we should have figured out that format to describe the dependencies. As far as it will come out after hey, we tried to use it, we tried to do it and realized that we cannot. There is not enough information. And again, the C++ ecosystem is so different, right? So everyone have to find a way how to talk to each other. So yeah, it would have been better, but we don't have it. And I think we have it in a standard, and now everyone have to a little bit talk, and that sparks some ideas and come up with something. Yes. More questions? Yes.
Going back to your demo.
Mm-hmm.
So what exactly have you been demonstrating? So what did you use to achieve this behavior where you don't need lots of boilerplate? Is this something between CMake, on top of CMake, some custom scripts? So how exactly did you build that?
In this particular case, what you've seen, it's on top of CMake in a way. But I have two versions. One on top of CMake, one is just a shell script, which is 100 lines. But again, if you look at this steps, anyone can do them. It's not a big deal. It's just okay, scan a file, get it. Scan a file, get it. And there was another talk at CPP Now by Bill Hoffman, also CMake guy, where he said that they think and that they want to drive the community that build systems should become just one build system, like a backend. Everyone should do this in a way the generic stuff that So the point was my demo that we can do better. We can be like Rust. We can be like Cargo in a way. And I'm not sure if anyone attended the Klaus talk about the real problem in C++. He was saying it's basically us and community, we have to drive it. We have to push us to do better, and we can do it, right? And this is just the purpose to show that it's possible. And again, if I go to mirror, right? I mean, wouldn't it be cool if you don't need to write anything? No, okay, you wrote the CMake TOML or something, or wherever it is, but then you just built. How easy it is to teach, how easy it is to use, and you don't need to worry about. Now you're in a way, in that experience like Rust and Cargo, right? You just use it. You can focus on your code. You don't need to worry, oh, I forgot to include, I forgot to guard it, I forgot that, and that. Now I just can use it. So that's the whole purpose, just to show that it's possible. Any more questions? Yes? Yeah, okay, the question is how to use, when we have the simplicity, how to use it with different configurations. Unfortunately, I don't have any good answer, because if you look at the Cargo, they have they call it macros, right? Or when you can disable, enable some features. So maybe we could use something the same. I don't know, I have not, but that's a very, very good question. And I think this is back to if we have a good ecosystem which talks to each other, maybe we'll already have a solution. Most likely you will have to learn how to do that. I envision in my mind that maybe some macros could be used here, but maybe not. It's hard to say for me, but very good question. Yeah.
In your example with the improved build times, you demonstrated how the bigger the number of files, the better improved.
Yes.
And you also mentioned tests. Well, you see, when we're writing tests, usually we single file is just modify, test, fails, try something else. So in this
Yes?
build and run loop. So basically, only one file is being built. And my question is there a way for us to expect some build-time improvement over?
But you can see it here. Even rebuilding one particular file is faster, right? 2 seconds versus 4 seconds.
It's a little bit strange because if you had the fourth column with the ratio
Mhm.
of build-time headers with build-time modules, it's almost around 1.52-ish each on each line, which seems a little bit deceiving to me. So here kind of doesn't really depend on the number of precision units. It's
Yeah.
strange and contradicts what you said
And,
before.
and what it contradicts to?
I mean, the ratio of the columns are more or less the same.
Yeah, but the thing is, you're building, and in this particular case, you're building in parallel stuff, right? You're not building it just by one. You're running, like we all build with many CPUs, right? We say run and GA2040, whatever you have, right? So that includes that. So you still build these two files in parallel. It's not like one by one. If you do it one by one, you will see significant speed if you just build with one job. I actually can show, if you want, we can sit down. I have this benchmark on my laptop and you will really see the difference.
Alright, so I feel like this table should go down and exceed the number of CPUs that you have to see how it changes.
Just go by the link and read, it has more info. I just took the table, you know.
Nice.
So,
Okay.
yeah.
Probably will.
And again, it's just their benchmarks, right? There was a talk on not CPP Russia. I forget which conference it was, but the talk was there that they actually in Eternal project they saw like 3 times X improvement of build time.
For a single unit?
No, for the whole project. Yeah. And again, it's a big project and combination of that all modules you built. It's a big repo, so yeah. Again, but of course you might don't see it on one particular unit. Yes. Yeah. Any more questions? No. Thank you so much.